Hello everyone, and I'm Timothy, speaking for my team's project, Electromagnetic Damping of a spring magnet oscillator using a Coil resistor load. So, have you ever seen a magnet drop slowly through a copper pipe? That's electromagnetic damping at work, the same principle which we explored in our project. As the title suggests, we build a spring magnet oscillator and use a Coil plus variable resistors to control how quickly the oscillations die out as shown in figure 1. And here's how it works. We hung strong neodymium magnets from spring of total mass about 0.224 kg and also spring constant of about 15.8 newtons per meter. The coil has about 210 turns of copper wire and the resistance about 3.2 ohms fixed right where the magnets pass through equilibrium. When we pull the mass down about 1.6 cm and release it, the magnet oscillates up and down. Running load, it rings for a long time, and that's mostly due to the air resistance present, which is a minor factor. And if we connect the coil to a resistor, the oscillations would decay much faster. That's due to the Faraday's law of moving magnets change flux through coil, inducing voltage and current, and by Lenz's law, the current creates a magnetic field opposing the motion, like an invisible brake. So, of course, we want to prove this mathematically and experimentally, so the motion follows the damped harmonic oscillator equation on screen, equation 1, which we split damping B into the mechanical part and also the electromagnetic part, as shown in equation 2. So, from the energy conservation and the Ohm's law, we derived that the electromagnetic damping is strongest when resistance is low. And our key prediction was that the total damping rate gamma is equal to the sum of the baseline damping rate plus a constant over total resistance. So you can see up here. So the gamma should increase linearly when plotted against 1 over total resistance. So we have tested 7 different load resistance from about 8 ohms to about 15,000 ohms and recorded the induced voltage with sensors set at 20 Hz and measured displacement from 4K 60 fps videos. The results match our theory beautifully, and we have got a damping rate of about 0.019 per second at high resistance to 0.286 at low resistance, which shows a strong linear trend. So this shows that the tunable electromagnetic damping would be useful for vibration controlling machines, cars, or even energy harvesting devices. And of course, we do had some non-ideal effects like minor resistor heating at low resistance, but the agreement with the theory was strong, where we have seen an R squared over 0.99. So the correlation is really strong. And that's it. So now, last but not least, thanks for watching.